Here we're going to go through the instructions on how to solve systems of equations. We start off by saying, oh, well, what's a system? What's going on? Let's just take a couple of lines here. Y equals 2x plus 4 and 3x minus y equals minus 1. So we take these things, and for this guy right here, we'll highlight him in blue. If we put him on a graph, we get 0, 4 is a point on that line, and the slope is 2 up 2 over 1, and we get a line. Now this line represents all of the individual pairs of x, y that will fit on y equals 2x plus 4. Now here, if we do this guy in red, we say 3x minus y equals negative 1, and graph him on the exact same thing, we have that 0, 1 works, and this has a slope of 3, 1, 2, 3 over 1. So this guy comes up here like this, and you'll notice that one point is purple, red and blue at the same time. This is what we call a solution when we put these two equations together. This has infinitely many solutions, this has infinitely many solutions, but when you put them together, these two lines, if they're not parallel and they're not at the exact same line, will cross in exactly one point. So this guy solves the system of equations. Now we could kind of take a guess and say, oh, he's over about 3 or he's over about 4 and try to figure out what it is, but there are a couple of different ways to do it. The first way is by substitution. Substitution starts out like this. We say 3x minus y equals a negative 1, and we say, well, what if y were 5? You know, fill out that little chart like we did at the very beginning of lines. Stick 5 in here, and we get 3x minus 5 equals negative 1, and then dot, 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 find x as its partner. What if y is 9? What do we do? Well, we go 3x minus 9 equals negative 1, and dot, 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 and solve it. So now we're doing this equation right here, but we're told that y equals 2x plus 4. So we do the same thing. We take that 2x plus 4 over there and thump, stick it right in. And we get 3x minus y. We now know what y equals a negative 1. And we solve this. The big secret of doing this is this equation had two variables in it. That equation had two variables in it. By getting y equal to something and sticking it in, we now have an equation that only has one variable, which we can solve. 3x minus 2x minus 4 equals negative 1. 3x minus 2x is x. Add 4 to both sides, and we get x equals 3. That tells us that this point right here, the x coordinate is 3 something. So let's find out what that is, and we can stick it back up into here. 2 times 3 is 6, plus 4 is 10. Y equals 10. You could stick it into the other guy too. Let's try that. 3 times 3 is 9, minus what equals a minus 1, and again we get the answer is 10. This is what substitution is all about. Let's try another problem. 3x plus y equals 5, and y equals 7x minus 15. there's one point that's going to take these two lines and give you a solution of both of them at the same time. So we're going to use substitution to do that. Here's what y equals right here, 7x minus 15. So this 7x minus 15 could go right up into that point right there. And we get 3x plus y, which is 7x minus 15, equals 5. We now have an equation that we can solve. This is 10x. Add 15 over to the other side, and we get 10x equals 20. X is 2. This gives us half of the answer. Let's draw a graph right now so we can see what we've done. 3x plus y equals 5. 0, 5 is a point. Oh, let's put that guy in red. 3x plus y, 0, 5 is a point. It has a slope of negative 3 over 1. So it looks about like that. And then this other one is y equals 7x minus 15. Let's put that guy in blue. 7x minus 15. So it's right here. Minus 15 is headed up really steeply. I probably got those slopes a little bit wrong. But what it does say is of this point right here, I don't know if it's going to be higher, above, or below that. I'm not sure how to tell that with that sketch. But we do know it's going to be 2 something. Well, let's find out what it is. Stick 2 in right here for x. 6 plus negative 1. Ooh, looks like I did a little bit off and it should have been down here. 2, negative 1. And here's how we do that substitution in. We take that and go right up there. 3 times 2 is 6 plus y has to equal 5. Subtract 6 and you get y equals a negative 1. Same thing, we could have stuck it right in there. 7 times 2 is 14 minus 15 is a negative 1. Either way it'll work. That's what substitution is all about. Now, for substitution, we would take and rewrite this as y equals 9 minus 3x. Then we would take that guy and stick it in there, down over here. That's what substitution does. I want to show you something new. Without doing that substitution, let's take those guys off and see what happens here. These are two equations. 3x plus y will always be equal to 9 in this system, and 2x minus y will always be equal to 16. If this is the same as 9, we could actually add this side to here and add that side to here. Now look at what happens when we add equations together. This becomes a 5x. The positive y and the negative y goes away. Equals a 25. You're like, can we really add equations? That's the idea of an equal sign, is that they are the same thing on both sides. So when we add an equation, we've added the same thing to both sides of that bottom equation. And in this case, we have eliminated the y. It is now gone. This method is called elimination. When you get rid of a variable by being able to do that. Divide by 5, and that gives us x equals 5. Like, yeah, that was slick. Those y's just went away. But it has the same purpose as what substitution did, and that is getting it down to one variable. So now we take this 5 and stick it up anywhere we want. Let's put it right there. We get 2 times 5 minus y equals 16. That's a 10. Subtract it over and get minus y equals 6. So y equals a negative 6. That means our solution is x is 5 and y is 6. That point works in both of them. And let's just double check. 2 times 5 is 10 minus a negative 6 is indeed 16. And 3 times 5 is 15 plus a negative 6 is 9. So 5 negative 6 actually works. Let's do another one with elimination. Here's another system down here. 2x plus 3y equals, and over here we're going to have x minus y equals, let's do a 13 up there and a 4 right there. Now, up here we just added them and they happen to go away. That was pretty slick. Down here, if we add them, nothing actually goes away. This is a 3x. That becomes a 2y, and that would be a 17. And we didn't really get anywhere. We didn't get rid of any x's. This is where we go back to the grand thing we learned about an equal sign in the first place. You can if you have an equation, you can add, subtract, multiply, or divide anything you want to both sides, and you get an equivalent equation. Wouldn't it be nice if this were a negative 3y? Well, then let's make it a negative 3y. Times everything here by 3. Now could we add these? You may wonder, did we really create the same equation? And the answer is yes. You could check that this has the same slope, goes through the same points. So we now have a system of equations where elimination is well set up. This is 5x. That goes away, equals 25. Well, that's kind of funny. Didn't plan that. But x is now 5. Good deal. Let's stick it in. We now have half of the answer. Let's stick it in. Let's go back to the original one where we had x minus y was 4. And we stuck in a 5 right there. So it should be 5 minus y has to equal 4. Means y in this case equals a 1. The answer then is 5 for x and 1 for y. You can just double check. 5 there and 1 there will indeed work. And 5 there and 1 there indeed will work. To the boards! Here are some problems for you to put in your video notebook. Pause the video and then turn us back on when you're ready to see how you did. Welcome back. Hope you did all right. Let's give it a try. Here, number 1, it says use substitution. So it is requiring us to use one of those processes, which is substitution. Well, luckily, we already have y by itself. So we're going to take 2x minus 5 and stick it in for the y. So we now have 3x plus 5 times y, which is 2x minus 5, equals 27. Now look at what just happened. We now have an equation that only has one variable. We know how to do that. It falls apart before our very eyes. 10x minus 25 equals 27. So add these two together and we get 13x. Add 25 to the other side and we get a 52. Divide by 13, and we get x equals 4. I think it comes out nice as 4. We are not done yet. We still have to stick that 4 back up in. You could do it into either one of them, and you get y equals 2 times 4 now, minus 5. So 8 minus 5, y equals a 3. So that means we have the point 4, 3. Good, there's number 1. All right, number 2, let's look at that one. Use substitution. Again, it's asking us to use this particular way. This one might be easier with elimination, but alas, the instructions say otherwise. So we're going to use substitution. We've got to get y by itself with one of these. They gave us an ugly problem. Dirty, rotten scoundrels. Let's take this guy out here and solve it for y. Subtract 5x from both sides, and we get 2y equals a negative 5x plus a 7. Divide by 2, divide by 2, divide by 2, and we get y equals negative 5 halves x plus 7 halves. Oh, fractions galore. But we're going to take that and stick it in to the y right there. So we get 3x plus 7 times y, which is negative 5 halves x plus 7 halves. That has to equal a negative 19. Ew. That's just disgusting. Well, we know how to do this. Remember our 5-step process. Are there any parentheses? There are. Let's distribute. So we get 3x plus, nope, not plus, indeed. That is minus 35 halves x plus 49 halves equals a negative 19. Okay, do we have any fractions? Well, yeah, that's the whole problem here. Let's get rid of the fractions by multiplying through by the least common denominator times by 2 everywhere, and we end up with 6x minus 35x plus 49x. Yeah, I like that. Those denominators just cancel, and that equals a negative 38. All right, so combining multiple x's, 6x minus 35x is a negative 29x, and then when we subtract 49 from 38, let's write that out a little bit better. 49 and a negative 38, that's a negative 87. All right, negative 87. I hope this comes out nice. Divide by a negative 29, divide by a negative 29, and we get x equals positive 3. Wow. Are we done yet? No, we got to find the other half of the point. We just found the x coordinate of those two, so let's come over here and stick it in. I don't know, we could go either one of them, but 5 times 3 plus 2y equals 7. 15, subtract 15 over there, and we get 2y equals a negative 8 by subtracting 15, and then y equals a negative 4. So we get 3 comma negative 4. Does that really work in both of them? 5 times 3, 15, plus a negative 8, indeed equals 7. 3 times 3 is 9, plus a negative 28 equals 19. This is the one and only point that works in both equations. So yes, indeed. All right, let's see if this one is any nicer. Solve. Oh, look at that. Just solve. That means we could use elimination or substitution. And oh, this is set up beautifully for elimination. If we add these two together, the y's will go away and we'll have an equation with just one variable. So let's do it. Add these two together. I'm going to put it like this. You could add them straight down. 2x plus 7x is 9x. 17 and 1, that's 18. So we get 9x equals 18. X equals 2. Oh, good. Now let's stick 2 back up in here. We get 7 times 2 is 14 plus y equals 1. That is subtract 14 from both sides, and we get y equals a negative 13. So the point is 2, negative 13. And that is the only point that works in both of those equations. All right, number 4. Solve this. Ooh, we can use substitution, which will get us these kind of bad fractions, or we can use elimination. I vote elimination. Let's try it. The y's we'd have to multiply by 8s and 5s. These we'd have to multiply by 2s and 3s to get them both 6s. I'm going to do that. Let's take these guys right here, times this guy by a negative 3, and this guy by a 2. Will that work? Let's write it out here just to make sure that's all right. Negative 6x minus 15y equals negative 27. And this one is 6x plus 16y equals 26. Huh, look at that. Okay, so if we add them, negative 3 times 2 and 2 times 3, that gives us 6 and negative 6. The x's are gone when we add them together. Negative 15 plus 16 is 1y equals, and then negative 27 plus 26 is a negative 1. So y is negative 1. Hey, look at that. So now let's stick it in and write 2 times x plus 5 times a negative 1, which is negative 5, is going to equal a 9. 2x, this is negative 5, add it over and we get 14, and x is 7. So we get the point 7, negative 1. Does that really work in the other guy? 3 times 7 is 21, plus 8 times a negative 1. 3 times 7 is 21, minus 8 is indeed 13. Good. Here's one of the most interesting uses, or maybe abuses, of systems of equations, is being able to turn decimals into fractions. Now, we know that any decimal that stops or repeats is actually a rational number, which means it can be written as a fraction. It's easy when it stops, like 0.5. What is that? Well, that's 5 in the tenths place, so that's easy to write, 5 tenths, and then we reduce the fraction and we get 1/2. Same thing with everything that stops. But what about when it repeats, like a 0.3 repeater, goes on and on forever like that? Well, we know that's going to be 1/3, but how can you turn it into that if you didn't know that? And it turns out that this system of equations thing turns out to be very valuable. If we know this number x is 0.333 on forever, we can actually manipulate this to create another equation that will help us. For example, times by 10. So 10x. Well, when you times by 10, the decimal goes over. And do we still have the same number of 3's? Yep, they go on forever. Now this is kind of, we only have one variable, but we've set up kind of a system of equations that will help us get rid of the decimals. If we subtract these two equations,
10x minus x is 9x, and 3.33333 minus the 0.33333 that we had before, we now have 3. Can we solve this? Indeed, x equals 3/9, or 1/3. And we've changed that decimal, which was x, to 1/3. Let's try another one that's not so easy. What if about x equals 0.4545 forever and ever, like that? Well, in this case, in order to use a second equation to cancel all those out, we'd have to times by 100. So we take 100x, and that equals 45.45 on forever. Like that. Yes. So now when we subtract them, we get 99x equals, and then that guy goes away with that one. It's gone completely. They go on forever and ever. So we now have 45 right there. So the idea of adding, subtracting equations, even though we only have one variable, that's what I kind of meant. It's an abuse of the systems of equations. Usually systems of equations solve for 2 variables, but here we're using it to write this number in a couple of different ways that will allow us to cancel out the fractional portion. So divide by 99, divide by 99, and does that guy simplify? Take out a 9, take out a 9, and we get 5/11. And you can try it if you took 5 divided by 11. Oh, yeah, 11 goes into 5. Nope, 11 goes into 50 4 times, and you get 44. Subtract, and we get 60. 11 goes into 65 times. 5 times 11 is 55. Subtract them, and we're right back to the 50. So it will repeat 4, 5, 4, 5 forever and ever. Fascinating that we can use those systems of equations to go back. Okay, now back to your regularly scheduled instruction.
So here's another example. This one, we have 3 equations and 3 variables, but elimination is so nice it allows us to do this. Show you what I mean. If we could find a way to eliminate one of these variables in 2 different ways, we would be able to, we'd have 2 equations and 2 variables which we could get. A picture of what's going on here is this is now, instead of a line on a graph, this is a plane, a flat surface through a 3-dimensional space. And 3 of them could intersect at one point. So that's what we're going to try to find here. Now, if you look at these, we look and see, oh, if we just added these 2, the y's would go away. And if we added these 2, the y's would go away. So I'm going to introduce some notation here. I'm going to put an arrow like this and say these 2 are being added together and making a new equation over here that I'm going to write. X plus x, that's a 2x. Y and negative y, gone. That's what we wanted to have happen. And negative 2z minus z, that's a negative 3z equals 3. Notice we now have an equation where y is gone. So we could pick any other way to get rid of a y if we wanted to. We could just add these 2 together, but for the sake of this notation, I'm going to show you another way we're going to do it. But you could just do that. I'm going to take these 2, and I'm going to times this guy by a negative 1. You could have just done these 2 and had another equation. That's okay. So negative x, because we times this whole thing by a negative 1, plus this guy, negative x plus 3x gives us a 2x. Negative y plus y is gone. That's what we wanted to do. And positive 2z, that's a plus 4z equals negative 3 plus 13 is 10. I'm going to change colors here one more time. And here we're back to where we were with the problems before. We have 2 equations and 2 variables. We need to get rid of one of them by elimination. Wouldn't it be nice if this were a negative 2x, or if that were a negative 2x? Let's make that one negative. So I'm going to take these 2 equations. I'm going to times this top one by a negative 1. We could get rid of these. We could have times this guy by a 4 and this guy by a 3 to make them both 12s, but this is a little bit easier. Negative 2 plus 2 is gone, and we have positive 3z and 4z is 7z. And here we get equals 7. That means z equals 1. Now, the reason I like this notation is the problem was huge, got a little bit smaller, got smallest. Now we have one answer. Now we go back here and say, okay, let's find x. 2x plus 4z times 1 equals 10. Now we have just one equation to solve. 2x equals 6, x equals 3. Now we have z and we have x. We move back one more step, and let's get y. So we could stick this into any one of them that we want. Let's choose the bottom one. So let's put a z right there. Let's put the x right there. So we have 3 times 3 is 9, plus y, plus 2 times z, which is 1, equals 13. 9 plus 2 is 11. So if we subtract 11 from both sides, we have y equals 2. That means our answer is x is 3, y is 2, and z is 1. One last thing. There are some odd duck answers you may get. Sometimes systems of equations, I'll give you an example really quick here, but sometimes they'll give you some answers and you're like, what is going on? You don't get an x equals this or a y equals this. If I had something like 2x plus y equals 9 and 4x plus 2y equals 18, you may think, wait a minute, all you did was times this guy by 2. I thought you said that gave us the same line. Yeah, if you were to try to eliminate something, you would get a statement like this. 0 equals 0. Now way back in the last unit where we did equations, whenever we got 0 equals 0, the answer was like all numbers. Well, what happens is we are trying to find where these two lines cross. And we got the answer 0 equals 0. Well, how often is 0 equal to 0? Always. These lines are always crossing, which for this, we don't have all numbers as a solution. We have this set of numbers, which is an infinite, huge, big set of numbers that works. So we just write down infinite number of solutions. However, similar to what we did before, if you should ever get something like 0 equals 7, or 0 equals 1, 0 equals 13, negative 26 equals 13,000, these are just false statements. These never happen. Which means that the intersection of both of these lines, or all three of these at the same time, will never happen. Or in other words, just like we did in the previous unit, there will be no solution. So those are the two kind of exceptional cases where you may end up with 0 equals 0 or some other always true statement, in which case you have an infinite number of solutions. And 0 equals 7 will give you no solution whatsoever.
To the boards! And to finish up, let's make sure you guys get the opportunity one more time at the boards. Pause the video, write down these problems, put them in your notebook, and then resume when you have given it a shot and need to check to see how you did. And welcome back. All right, here we go. Whoa, this has got 3 equations and 3 variables. That's good. But notice that these are already solved for the x's. So actually this one will be valuable with substitution. So 2x minus 7 goes in for y, and x plus 2 can go in for z. So we actually have x plus 2 times 2x minus 7 minus 3 times x plus 2 equals a negative 16. Substitution, especially in word problems, will come in handy. So don't forget that you can substitute, and that'll work. We'll use elimination down here, but this one was set up for substitution. So x plus, get the fractions done. You get 4x minus 14 minus 3x minus 6 equals a negative 16. How many x's? X and 4x and minus 3x, so that'll give us a 2x. Minus 14 minus 16 is a minus 20 equals a negative 16. So add 20 to both sides and you get 2x equals 4. x equals 2. We're not done. We got to stick that back up in there. So what does that mean? We have y equals 2 times 2 minus 7 equals 4 minus 7 is a negative 3. And z equals x is 2. So we have 2 plus 2 is 4. So we have 2, negative 3 is y, and 4 is z. So that is our point of intersection of these three equations. Good. Now let's move on down to this guy right here. So we have a system of three equations. So we have to pick a variable to get rid of. The z's would be nice to get rid of. We could add the two bottom and then add the bottom and the top, and the z's would get rid of. The y's also kind of easy. The x's not as easy. You'll notice we would have to times the middle one by a negative 2 to eliminate the x up here and negative 3 here. Let's go ahead and do the y's right now. So if we add these two guys together, then we get 2x plus x is 3x. The y's eliminate. The z's become 2z equals, and 12 plus 5 is 17. Now we can take the top one times 2. Yeah, the top times 2, add it to the bottom one. I'm going to write it like this, and take this guy times a 2. So that'll remind us to do that. So we get 4x plus 3x is 7x. The y's, negative 2 plus 2 are gone, indeed. 2z minus z, that's plus 1z, equals, and 2 times 12 is 24, plus 12 is 36. Notice that when we went back to multiply this by something and times it so we could eliminate this, we went back to where it was before, not worrying about what we had done to get the red equation. But now we're going to take the red and the green, and that makes brown. So let's use brown for this next one, and we got to pick a variable and eliminate it. It looks like the z's are easier than the x's, and if we take and times the bottom by a negative 2. So let's do a negative 2 right there on the bottom one. So negative 2 here, 14 plus negative 14 plus 3 is a negative 11x. Negative 2z plus 2z, they go away. That's why we picked a negative 2. And negative 72 plus 17. Ooh, that is a negative 55. Oh, I'm glad it comes out. Divide by a negative 11, divide by a negative 11, and we get x equals 5. So when we take and go back a step and stick in 5 for x, we now have 7 times 5 plus z equals 36. Subtract 35 from both sides and we get z equals 1. We now have two of the variables, so now we're going to stick to find y. And I guess we could pick any of them we wanted, but I'm going to pick z to go right in there, and we'll pick the x, 5, to come over here and go right in there. And then let's see what we have when we write it down. We have x, which is 5, plus y, plus z, which is 1, equals 5. 5 plus 1 is 6. Y plus 6 equals 5. And subtract 6, and we get y equals a negative 1. So our answer is x is 5, y is negative 1, and z is 1. Oh, good. That is the point that will work in all of them. 5, negative 1, 1, 5, negative 1, 1, 5, negative 1, 1. And it's the only combination of three numbers that will work in all three of those equations. All right, let's look at number 3. Here, number 3 and number 4, we put in here to make sure you had some practice with no solution, all real number. Let's see if you got it right. So in elimination, do you want to get rid of the x's or the y's? Let's get rid of the x's. We'd have to times the top guy by a negative 2. So negative 4 plus 4 is 0 x's. Okay, good. The y's, negative 6y plus 6y is 0y, so we get 0 equals negative 16 plus 8 is a negative 8. 0 equals negative 8. You should feel very weird having written that, and yes, indeed, that is a no solution. That will never happen. These two are actually parallel lines that go through different intercepts, so they will never cross. That means there is no x and y coordinate that will work in both of them. All right, number 4. Let's do it again. Let's times the top guy by -2. It's almost the same as the system up there. We get -4 plus 4 is 0. -6 plus 6y is 0. So we get 0 equals -16 plus 16 equals 0. This one is true, and it's always true, which means that these two lines are always crossing, which means you have an infinite number of solutions. In later math classes, you will be able to write down what those solutions look like. It might be the line here in this case, or if you have a three-dimensional one, it might be a line or it might be a whole plane. But right now we'll just settle for infinite number of solutions. Infinite number of solutions. Good. And there you go. Good luck with the homework.